Hello, everybody. I thought I was going to get the triumphant fanfare music while I was setting up the laptop, but I guess not. I'm delighted to be here today. Thank you guys for having me here. Many of the other talks have been about very concrete technologies that you use every day and about exciting topics. So I'm here to talk to you today about how to write great code, and I've got some ideas about that. But in order to get your interest, considering it's after lunch, let's talk about nuclear war. So as it turns out, a software system in 1960 was looking over the horizon, looking for an oncoming attack, and it detected one. It alerted all the human beings. And the humans decided this was really unlikely, and so they ignored the software, thankfully. It turns out what had happened was that the moon was rising, and when they sent the radar over the horizon, they got all the reflections coming back and thought it was a nuclear attack. Does anyone else write this software? I hope not, because this would make me very nervous. Now, when you think about what went wrong, there's a bunch of superficial explanations. You could say, well, there should have been more tests. They gave us bad requirements. There were bugs in the code, and we know that always happens. Or perhaps they should have used my favorite language, my favorite process, or whatnot, okay? But there's a deeper answer in terms of what went wrong in this particular case, and that is that every program at the core of it does not manipulate the real world. It does not sense the real world. It's manipulating symbols inside of it. And if you have a bad model of the world, if your symbols are bad, then the program is going to do crazy things like this every once in a while. So the author of this paper, Brian Cantwell-Smith, he produced this diagram to help us think about it. And what he shows is that the computers don't work on the real world directly. They work on a model that we've created for ourselves. The computer itself is running software. And what is it doing? In our cases, it might be doing pedestrian things. It might be landing airplanes, playing videos, or running this conference. And when our software is doing that, it's operating on a model of the real world. The symbols come from the model, and it's hard to imagine a computer program actually operating on the raw, real world itself. Just as a thought experiment, imagine what the computer's really doing, and imagine if it were trying to operate on the real world. Even the zeros and ones inside of our programs are actually abstractions of voltages on wires. It's not really 0 volts for a 0. It might be 0.1. And it's not really 5 volts for a 1. It might be 4.8 or something like that, but it's close enough, and so our model collapses those into either zeros or ones. And it turns out that symbolic representations are essential for us to reason about things. Now, resorting to some clip art to make a point, let's imagine that the person on the left was raised as a caveman, or it's the same person raised on the right-hand side. And what we can tell, besides the fact that he has a better haircut on the right-hand side, is that he has some abstractions in his head. He has a model of the world. His model includes things like houses, condos, and apartments. And he might ask his alter ego, the caveman, can you help me? I'm trying to decide where I'm going to live. The caveman only has one concept. Caves is about where you can live. Whereas the other guy, he's got this rich model of the world. He's taken all the phenomena of the world and categorized it. Now imagine that we brought the caveman to today. He could see houses, he could see condominiums, and he could see apartments. He's physically able to see those things, but if his mental model doesn't include them, he can't operate on them, he can't process them. So in the same way, our computer programs are operating on models that we choose to interoperate with. The models themselves do not have all of the details of the real world, and they can't, by definition. Otherwise, we'd have to be worrying about whether it's 0 volts or 0.1 volts. So we're always in this difficult search where we want to say, if I put more details in the model, I can talk about more things, I can operate on more things, my logic works on more things. But the simpler models are what allow me to actually make forward progress. So you might think, George is talking about some pretty esoteric things, some pretty out there things. So let's get back to like a mundane kind of problem that many of us solve. Let's imagine I have something really simple, like I've got customers and addresses. Does this resemble kind of programs that many of you work on? Okay. So the first problem with this model that might come up, this is your first version you code up, is you might say, well, actually, there's a billing address and the shipping address, and those are different. So I've got to change my model. I've got to make it richer. I've got to express more of the world inside this model. And so I do that. Well, as it turns out, when you get together for the holidays, sometimes you want to ship packages to the place where everyone's getting together. Well, that seems convenient. So we call this shipping in care of somebody else. And so you have to elaborate the model again, except this time you now have many addresses for a customer. Well, it gets worse, because as soon as you allow that to happen, what if two people at the same address are both customers of you? Well, now I've got to change the model again. I've got to make it allow more cases into it. And then you decide, actually, I don't want to deliver packages to the post office, and so I elaborate my model once again. And then I ship some boxes to some place, and I find out that that address is a valid address. It's just not a valid address for that customer anymore. He doesn't live there. And so at that point, you have to throw this model away entirely, because you've got valid addresses, valid customers, but that they don't link up correctly. And how do you encode that? OK. Point being, these are the kinds of things we deal with bread and butter as software developers. And what we're really doing is we're enriching not the software itself. So far, there's no software. We're enriching the model that we have of the world. So last year, I was in San Diego, where the ship exists. And it was nighttime, and I was walking along the sidewalk, and then I see this ship. And I'm like, what's the ship doing buried in the dirt next to the sidewalk? And I look, and there's a plaque. And I read the plaque, and I saw the most amazing thing. This ship is used for training naval officers. Naval officers were assigned to the ship when they were doing training. Makes sense. The ship was commissioned in 1949, but it was decommissioned in 1967 because the software that was listing the ships and listing the officers, and it was assigning ships to officers, could not account for ships that were not in oceans, because all ships had to be in oceans inside the software. So they decommissioned the ship so that they could fit it into their software. Okay? So the crazier thing, perhaps, is that because this thing is sitting on land, it's like a building, and it has a front door, and it has an address where you can deliver things. So it's the only thing in the naval system that is listed as both a building and as a ship. Something you wouldn't have expected. So I'm inspired to talk to you guys about models because of a great essay that was written in 1985 by Peter Nauer, Turing Award winner. And this is a sentence from his introduction. It says, programming properly should be regarded as an activity by which the programmers form or achieve a certain kind of insight, a theory of the matters at hand. And then here comes the crazy part. This suggestion is in contrast to what happens to be a more common notion that programming should be regarded as a production of a program and certain other texts. So let me break that down in plain English. He says, I think programming is about inventing theories. Other people think programming is about building programs. All right. So here's my suggestion. Don't tell your boss that you saw this slide, otherwise he won't let you come next year. But it begs the question, what is this guy talking about when he says that it's really about building theories? So imagine this. Imagine there was a tragedy at work, and for some reason, your entire source code repository was wiped out and there was no backup. But the team was still around. You guys are still there. How long would it take you to reproduce the program? Well, certainly not longer than the first time, but most people would answer that it would be substantially shorter than the first time you built it. And the reason for that is because there's been a change in your head. You and the rest of the team have been chatting about this program, and you've been building up an idea about how it works. You've created a model of the world, and you've encoded it in your software. And you have chatted about different design ideas, and you've made them visible in the software. So really, this theory is a very valuable thing because it allows you to write the same software much faster than you did before. I would love to show you an example on this slide that shows source code that ranges from a little bit of theory in the code to a lot. But it's hard to write a lot of source code on one slide, as you might imagine. So I'm going to use something that's pretty close. Imagine you have this very simple spreadsheet. And as you can see right now, it shows the names of some months, a total, some numbers, and it says sales. And maybe the thing that's coming out of this spreadsheet that's really important is this number 42. Okay? Well, I could simplify this. I could write down less. I could write down this. I could remove the months and the total. Now, based upon what you know on the right, this still makes sense, doesn't it? Right? You still know what 14, 16, 12, and 42 represent because you know the thing on the right. The thing on the right is now in your head. Well, what if I wrote down even less? What if I just wrote down the numbers themselves? Well, it still works. It's like notes you would take for yourself, and you are leaving more of the theory in your head, and you're putting less of the theory on paper. Well, you could go the other direction. You could write down even more on paper. And in fact, maybe something here surprises you. Those were not sales, those were forecast sales, and the numbers represented millions of dollars, which you didn't know before, okay? Or you could go completely the other direction and say, I'm just gonna write down 42. That's what I really cared about, and leave all of the model and how I computed it and what it represents inside my head. So we always have this choice about how much model escapes our head and is on the paper, okay? So let me ask you this question. If you were working on a team of other software developers and you just wrote down 42, how much of that model that's in your head are they going to be able to recover from 42? Less. Certainly less than the thing on the right. So when considering this, Peter Nauer said, actually, if the programming team goes away, it's impossible for anyone to recover the theory of the program. He says the death of a program happens when the programmer team possessing its theory is dissolved. Does anyone else feel depressed about this? That your program dies when the team goes away and does something else? Is there probably a little bit of you that says, no, what if I write really, really good code? I'm going to write really good code, and it's going to not die. So then the next question you've got to have is, how do I write good code? How do I write code such that it doesn't die if the programming team goes away and does something else? So my answer, and this is not the only answer, but I think it's a pretty good one based upon what I'm structuring here, is that what you're trying to do when you write good code is you're trying to embed more, rather than less, of the theories that are in your head, make them visible in the code, embed them in the code. And when you do that, that is what good code represents. So going back to the diagram we saw before, we can think about this in terms of two dimensions. The first is teams, and the second is time. And by teams, I mean that software today is rarely built by a single person. And by time, I mean that software is rarely written once and then never changed again. Okay? And those two dimensions are the ones you should test whenever some guy like me comes up on stage and says, here's the way to write good code. Okay? So to make that concrete, let's try a little example. Here's some really simple code that you might write if you were writing some hospital software. Okay? So you've got a patient, the patient has a name, and there's a Boolean in there that says whether you should try to save them if they start to pass away. Okay, kind of serious stuff. It's going to get worse. So imagine I took this program and I took out all the names. Does anybody do this to their JavaScript code? And why do you do that? It's because, I would argue, you're trying to remove as much of the theory from your program as possible. Because the code still runs just fine. It still operates as a machine just fine. But the theory has been removed from the program, okay? Okay, do you feel better now? The names are back in the code, okay. So I'm going to do something even worse. Okay, so now, does this program run? Of course it runs. Do I know that that Boolean represents do not resuscitate? Of course, I know. Does the rest of my team know? No. And in fact, for a while, it's going to be just fine. But at some point, you know something horrible is going to happen if I do this to the code, right? It's going to be horrible, and we don't want that. So hopefully I've convinced you guys with gory graphic examples of nuclear war and patients who are vegetarians that you like really, really want to express your theories in the code. So let's try to do that. I'm going to argue that there are 3 aspects of your theory that are valuable to express in the code. Those are the design, the domain, and the argument about why this design has the desired effect on this domain. So here are some examples of things from the design, and these are terms that every one of us as software developers are going to recognize. Tables, foreign keys, lambdas, monads, servers, JSON, streams, clients, servers, any of these kinds of things. These are design topics that any programmer should understand. The second bit is examples of things from the domain. Customers, addresses, ships, doors, oceans, launches, things like this, okay? Now, these are not things that you knew about before you joined your current company, but anybody else working in that domain, they would understand those things, okay? So your subject matter expert or your product manager would know these things. So both of those should be in the code, visible in the code, recoverable by your teammates. And of course, there's things that overlap. So we have a customer table or an employee microservice. But perhaps the thing that isn't always so obvious until you get into a company where you have to do peer code reviews. Do any of you guys do peer code reviews? Maybe a quarter, maybe less. Is that if you start reviewing other people's code, you'll recognize that, sure, maybe this code works. But when I try to review it, it's very difficult to recover what was going on in your head that made you believe that it works, okay? And so having an argument in the code that makes it really obvious to everybody else why this works and why I put these things in this design just this way is actually really valuable on a team and over time. So here's my short way of trying to convince you that this is true. Imagine 2 little snippets of code. Okay, the one on the top uses a for loop, and the one on the bottom uses a for each. Okay, forget about the programming styles and everything else that's embedded here. What I want you to consider instead is, as someone reviewing this code, do you have confidence that every sailboat is sailed in this particular example? Well, in the second one, you hardly have to do any work in order to recover that argument. In the first one, I hope it's accurate, but it just sort of depends on whether the sailboats are initialized by 0 or 1, okay? And then you go, well, I think they're initialized by 0, so this code looks okay, and so forth. One way you can make better arguments to you and to your coworkers is to upgrade the kind of argument you're making. So this is an example of upgrading by using lambda expressions, okay? But otherwise, we can imagine reasoning through the code by mentally animating it in our heads, or by using class instance kinds of things, like sailboats are a class of thing, I'm holding on to a sailboat, which is analogous to the old philosophical argument about Socrates is a man, all men are mortal, therefore Socrates is mortal. But there's other things which are not as intuitive. Induction recursion we use in computer programs, you basically have to learn that. It's not something you're born with. Same thing with De Morgan's laws that let you rearrange logical expressions that are equivalent. I had to learn that in school. And then try-catch blocks are just not even something that non-programmers understand, but you can use them to make an argument to your peers that actually I'm going to handle exceptions just right. If the file doesn't get closed, I catch the exception and I do the right thing. So what I'm saying here is, if you want to make clearer arguments, you should consider upgrading the style of argument you're making in the program, not just asking them to follow through all the statements in your code. So here's an example of some code I ran across recently. I just want you to glance at it for a couple seconds. And one of the things that I'd like you to reflect on is that when you read it, you're trying to recover the theory that exists inside of it. And right now, you're asking yourself, maybe some of you already figured it out, like, what does this code do? And how are you doing that? How are you figuring it out? What this code actually does is it's written in Rust, and it's written on a Raspberry Pi without any base libraries. And what it does is it blinks an LED on a Raspberry Pi. Okay, no big deal. Sort of the hello world of Raspberry Pi programs. But the point I'm trying to make here is that there are ways that this programmer has encoded some things that were easy to find out, and there are other things that are in this code that you could say, if my intention was really trying to make sure that everyone on my team understood why this works, we probably could do some things inside this program to make it more obvious why it works. So I don't have time in this talk to talk about how you express design, but luckily I wrote a chapter of a book on it, so plug that. There's also a couple of talks on that topic on my website. So, in conclusion, first, I would like to help you write better code. I want you to write great code. There's 3 ways to do that, as far as I'm concerned. First, express your domain model in the code, because, as we said, all programs are working on models that represent the real world. They can't work on the real world directly. So what's in that model is not just some unimportant detail of some part of software design that you don't have to deal with, because you might say, I write the code, somebody else gives me requirements. This is really critical for you to get right. There's a particular point here I want to make at the end, which has been, many people have been talking about this recently, is in your program, you want to make impossible states from the real world, like this customer is -1 years old, impossible to express in your program. Because if you do that, then that's one category of error that you can't make. The second way you write good code is to express the design in the code. The first problem there is you have to have things to express. If you are somebody who hasn't read any of the programming books, if you don't know the design pattern names, if you haven't read the distributed system patterns, then you're going to have a hard time encoding that language in your program, even if your program works. And finally, I'm going to ask, you want to express your argument in the code, and you want to make it as clear as possible for somebody else to recover. On that point, I'd say, consider upgrading your logic to functional programming. Okay? This is not a hard sell on this thing, but one of the things you're noticing is that these kinds of constructs are increasingly present in mainstream languages, and there's a reason for it. It's easier to recover the argument if you do that style of programming well. This talk has been about model-minded development, and that means that I have my mind on my models and my models on my mind. You're supposed to laugh more for that. You're not supposed to clap, but okay. So what we have is a diagram from 1985. Brian Cantwell Smith saw a software failure, and he didn't take it to the superficial level that says we need to test it or we need to remove bugs. Instead, what he said was, let's think about this hard, and we'll realize that the software can only be as good as the models that we put into it, because it's manipulating models. Let's make sure we get good models in there. And on the right-hand side, this is the little diagrammatic depiction of make sure that your domain's encoded, your design is encoded, and that the argument is expressed clearly. And with that, thank you guys very much. It's been a pleasure being here.
So thank you. Thank you very much, George, for the wonderful talk. Ladies and gentlemen, make some noise for George Fairbanks. I think we ran out of time now, so we're back on schedule again. So there's 1 minute left. We could do one question if you like.
That'd be great.
And I'll ask this question straight away. So there's a connection between technical debt and what we've heard right now, right?
Yeah, most of you are familiar with the idea of technical debt. This is a term coined by Ward Cunningham. He was working on a financial system, and at some point, he recognized that the code that he'd written was expressing a model of financial world which was not quite right. And so he went to his boss and he said, here's the deal, we shouldn't stop everything, but we should treat this problem where the code and the model are misaligned, we should treat that as a technical debt. It's something that we have to keep paying for every day until we fix the alignment between how I think about the world and how the code works. But it seems like a great connection here, because most people think of technical debt as bugs in my code or ugly code that I wrote last week or ugly code that my coworker wrote. But instead, it's better to think about it as the models you have shift over time, but your code can't catch up quite as quickly. So that's the connection there. Thanks for the question.
Thanks. OK, I think let's do a roundup here. One last time, make some noise for George Fairbanks. Thank you.